Hello and welcome back to FEM Expert. In today's tutorial we're going to show you how to perform a harmonic analysis of a simple structure utilizing Ansys APDL. We're going to go straight to the model. We have here our Ansys interface, and we're going to look at this text file in which we're going to create an element type 181. It's a shell element. We're going to define the material properties of a steel in the international system. Then we're going to create a section of 25 millimeters for a shell. Then we're going to create the shell with the area. I'm going to copy this up to here so you can see exactly what has been done. So here we have the shell. We have the key points, we have the shell, and we're going to embed the shell on the left, on the line on the left, and then we are going to perform a model analysis and then a harmonic analysis to understand and to show you how to perform this type of analysis. So for the moment, what we're going to do is go to the text file. I'm going to resume here, and I'm going to go to the text file, and I'm going to perform the whole copy and perform the whole analysis. So here are our frequencies. We have all of these model frequencies. We're going to look a little bit on the model shapes. So I'm going to go and do under general post-processing set, 11, and I'm going to check on the results of the first mode, PLVect. That comma U. This shows you the deform shaped in vectors. So as you can see, this is deforming one way, it's going down. And we're going to do set comma next for the second shape. We're going to analyze this deformation. As you can see, it's twisting around the x-axis. I'm going to look at the next one, and as you can see, it's just providing us the results. Well, when performing model analysis, it's necessary for you to understand that first of all, you obtain the model frequencies, and second of all, you obtain the shapes. That's the only information that you can obtain basically, or like the most fundamental information that you can obtain from model analysis. There is other information that's more complex, but that's not the case of this tutorial. And if, for example, if you want to see what happens in between these frequencies, you cannot. And also the deformation values, for example, here, we're going to look at this scale, 1, As you can see, the end of this, our plate is deforming 0.41 meters. And that could not be possible. That is extremely low. We're going to go back to this scale, auto. These values are obtained from calculation because we're obtaining the main vectors, the eigenvalues. So they only are good for evaluating the frequencies and the shapes. So what we're going to do today is perform a harmonic analysis. For that, we're going to go to the A-plot, and we're going to introduce a force in one of these key points. So we're going to go to solution, Fk, P. We're going to go here, and we're going to say that we're going to introduce an Fz force of 1 Newton. So we have this force of 1 Newton that's on the corner of our model. And we're going to go to analysis type under solution, new analysis. We're going to go to harmonic. Okay, and then we're gonna go to analysis options, and not in here. Sorry, no, we don't have these options. We don't need them. We're gonna go to load steps and options, and then we go to time and frequency and sub steps. So here we're gonna go and we're gonna put 0 to 500, and the number of steps are 500. So what this simulation is going to do is going to perform a simulation with this force of 1 Newton from 0 to 500 newtons, 500 hertz, modifying it on 500 steps. So it's going to perform a simulation for each hertz, meaning this force is not changing in amplitude or force, but it's changing in frequency. So we hit OK. Oh, then, I'm sorry, I forgot. Then we have the ramped or the stepped. We're going to do the stepped option on this situation. They're not very high differences. It's just very specific. There are some very specific things on this. We're going to talk about them in later tutorials. So we're going to just go stepped so we don't get a warning message. And then we're going to do solve and solve. And if you go to the Ansys window, you're going to see that Ansys is performing one simulation for each frequency according to the information that we introduced. When we have it, the solution is done. If we go to general post-processing and you go to read results, and we go by peak, you're going to see that there's two results for each frequency. One are the imaginary results, and then the other ones are the real results. If you read the first line, they're the imaginary results, and if you try to see the results, it's backwards. If you read the second ones, you're not going to obtain results. You're going to obtain something like this because they are the imaginary values. And if you look at the real results here, you're going to see that you obtain these values. So this deformation corresponds to the effect of the 1 Newton going on the z direction when that force has it's a frequency of 2 hertz. So here we're going to look at, for example, at 85 hertz. One of the things is because we've been having this step increment of 1 hertz, we can look at these values, but we're not going to be able to catch the 85.537 frequency because we will be either on 85 or 86. This should be good enough in most of the simulations. If you need to obtain a specific or very detailed effect of a certain frequency, you will have to perform something like a simulation between 85 to 86 hertz and check how important is this peak for, I don't know, 1,000 values between those two frequencies or something like that. So we're going to go to here by peak, and we're going to go to 86, and we're going to check what's the deformation. So we read the first one. And as you can see, the deformation is basically the same as the one we had. And the one we had before in the previous simulation in the model analysis. And it may completely make sense. It's basically telling us that regardless of how this force is introduced, if the frequency is 86, our structure is going to behave like this. I'm going to go and pick up the 356 frequency, and again I'm going to check what's happening. And here's something interesting. Despite the fact that the force is introduced at the corner and is going upwards, this structure at this frequency does exactly the same. It has exactly the same shape, and it does exactly the same thing that we had under the model analysis. These frequencies, this analysis can be quite complex, and they can provide a lot of information. Right now, we're just going to check two things. And in later tutorials, we're going to analyze multiple different things that you can do with this type of analysis. And one of the most important things that you can do with this type of analysis is analyzing the displacements of the structure. So we're going to go here, and we're going to do the time his post-processing. Here, we're going to move this. We're going to take 2 nodes. For the degrees of freedom, we're going to go to the Z displacement. We're going to take this node, apply, and then we're going to take another node, more on the front and maybe onto one of the sides. So we have these 2 nodes, and if we select them with the shift and then hit graph data, what we have here is the results of the under a linear scale displacement that these points have obtained in the structure. As you can see, there's 2 peaks that correspond to the 2 peaks that we have here among the first 500 hertz for 85 and 356. And well, this is not too obvious right now, but if we plot the first one, we're going to see the same behavior. It's just the amplitude that's changing. And if we plot the second one, it's exactly the same. So this structure has, if you can see here, there's a little peak. It's just the difference between amplitude that is masking the effect of the, it's not allowing us to see properly that the curves are exactly the same. They're just overlapping basically with different amplitudes. these results are quite interesting. We're gonna keep obtaining some simulations with harmonic analysis in order to understand and view better things and see more information about how to perform this analysis, what they're useful for. So for today's tutorial, we're gonna stop here. We thank you very much for your attention. If you like our tutorials, please subscribe to our channel and hit the like buttons of our videos. Thank you for your attention.